Hello! It has been a little while since my last video, but I have been spending a lot of time working on and thinking on how to present this video because I realized that in a lot of my videos, especially my life cycle of stars video, it's quite important to be able to understand what the mass of objects that are very far away and very heavy are, but I've never gone into the actual methodology of how somebody could actually weigh a planet, for example. So that's what we're going to do today. We're going to talk about how you weigh something that you can't just plop on a set of scales. And if we're willing to go back a few hundred years to the late 18th century, we can find somebody who thought, well, why not just do the opposite? Because back then, in the late 18th century, Henry Cavendish made this device, which you can tell apart from a guillotine only from its lack of blades. It is made up of a lot of stuff, obviously, but the parts that we're really interested in are the two wires that hang down and then the lead weights that are suspended at the bottom of them. Before Cavendish performed his experiment, he measured how much force was required to bend the wires that he used in this apparatus, and then once he had the lead weights strung up by these wires, they would actually bend the wires very, very slightly because things don't have to be as big as a moon or an asteroid or anything like that to actually have gravitational forces acting on other objects. Any two things that contain regular matter, none of that like weird dark matter or anything, will produce some kind of gravitational force and attract other objects towards them. So he already knew the mass of these two lead weights, and he could then measure how much the wire was bending and measure how much gravitational force they were producing on each other. And then by comparing this to the amount of force going on between the lead weights and the Earth itself, he could determine how much the Earth weighed. So no offense to Cavendish or anything, but while this is great for measuring the mass of the Earth, and then now in the present day when we can actually send probes to other planets that are nearby like Mars, we can use the same method to measure them. But most of the planets in the known universe are significantly too far away for us to use this method. So we need something a lot larger that can be viewed from a long distance away to help us measure the mass of planets that we just can't physically reach. And for this, the best option is if that planet has at least one moon orbiting it. Technically, this can also be used for planets that don't have a moon orbiting them if there's another planet orbiting the same sun, but then it comes down to like weird subtleties in how the orbit changes very slightly when it passes by the first planet, and that would just be very boring and very difficult to explain. So we're going to talk about moons so that we can just understand how this actually works. And how it works is, you may have heard the concept before of an escape velocity. So when a satellite is launched into space, it has to be launched at a certain minimum speed so that when it eventually reaches the top of its arc and it starts falling back down to the Earth again, it will actually be going so fast sideways that it, even though it's falling, will never actually fall down to the Earth. So you can think of it like the satellite would be traveling in a straight line and the force of gravity is then pulling it sideways into an ellipse around the Earth. And the same thing is true for moons. After all, they are just natural satellites. And the other thing we need to think of is the very famous feather and bowling ball experiment. So if you drop a feather in a bowling ball and a vacuum, then they hit the ground at pretty much exactly the same time, because the gravitational acceleration on them, the speed at which they fall down, is not dependent on their masses. The only reason a feather typically takes longer to fall down is because air resistance has a greater effect on it. And obviously moons in outer space are not affected by air resistance. So if we can measure their acceleration, we know that we never have to worry about how much the moon actually weighs when we're thinking about that. But we do actually need to worry about another mass when we think about the acceleration of a moon, or any other satellite in fact, which is the mass of the planet itself. And the reason we have to take this into consideration is if you think about Newton's second law, F equals ma, sorry about that, force is mass times acceleration. So that mass would be the mass of the moon, and then the acceleration is everything else. But as we saw in Cavendish's experiment, he found how much force gravity produces first and then used that to find Earth's mass, because gravitational force does depend on the mass of both objects. So if the mass of the moon doesn't depend on the mass of a planet, which obviously it doesn't, then the acceleration has to depend on the mass of the planet, because that's the only thing left in the gravitational force equation. So if we can find the acceleration of a moon orbiting a planet, then we can just work out how much that planet weighs, because the only other factors that we need to take into consideration are how far away that moon is from the planet and the gravitational constant. Obviously, if we can measure how fast that moon is traveling, we can measure how far away it is from its planet, and the gravitational constant is a constant. So there's literally no reason to worry about that at all. And that brings us to the end of the video. I hope you enjoyed it. I'm sorry for how long it took me to get this out. I've been very busy lately, and also because of how busy I've been, and I'm going to be a lot busier in the future as well. There is going to be a video next week, but it's going to be in a very different style for this one, but it's still going to be space-based. I'm sure you'll enjoy it if you've been enjoying my other videos, and I hope you look forward to it. As usual, if you have any questions or anything you want to say, feel free to leave that in the comments below. And I've linked articles related to today's subject if you want to read more. If you guys want to know why I like space so much, it's because I actually recently moved into a void of pure grey, and I miss the sky.